Swayam Prabha. Digital India. Educated India.
Okay, we have been talking about stability theory, and we came to receptivity theory. We focused our attention on wall excitation. We specifically made a point that stability theory, the way it has been formulated and solved, refers to excitations which remains buried inside the shear layer. So that basically tells you that a huge area remained blank, and that area is when your fluid dynamical system is excited from outside the shear layer. Okay? And this is what happens. Let us say talk about a prototypical example here, and what we need to do here is consider a shear layer growing on a flat plate, let us say, and then we have a wall exciter here. As usual, we have done this before, but in addition, let us say we have a sort of a convecting vortices. We have a convex vortices, series of them coming, or maybe a single vortex coming. So, let us consider a case of a single vortex which is convecting at a constant speed c at a height capital Y, and at t equal to 0, this vortex was, let us say, a little upstream of the leading edge. And then once this vortex starts going, then what happens? Recall that in spatial stability theory, what we had done. In the spatial stability theory, what we have done is we imposed a time scale, and then we saw how the disturbance grow in space. That was the whole idea. So, in this case also, we are imposing a time scale here through this wall vibrator. That is one thing that we can see. Now, what happens to this additional exciter in the free stream, and that is what we have started discussing over the last few lectures. And what we saw, that the existence of that line vortex of strength gamma moving at a constant speed c at a constant height a y gives rise to kind of a disturbance stream function, and this disturbance stream function provides a kind of a free stream excitation. And now, if you recall, what happens is that we have this 4 fundamental modes of Orson field equation, right? We have this 4 fundamental modes of Orson field equation, and then because now you have to satisfy the boundary conditions not only at the wall, but also in the free stream. So, you will be perforce have to keep all these 4 modes with this multiplicative constant C1, C2, C3 and C4. This is what we are doing. We are defining the disturbance stream function in terms of its Laplace transform, and those are again split in terms of the 4 fundamental modes. Now, once you do that, what you are going to get is 2 sets of boundary condition at the wall. One corresponds to u equal to 0, that would imply the primed quantity, means derivative with respect to y, that should be equal to 0. And this is the wall normal component of velocity, which is located at x equal to x naught, that gives you this delta function, and it is a harmonic excitation at a frequency omega naught. So, that is what you get e to the power minus I omega t. And this I could write it like this, right. This is exactly the representation in the Fourier Laplace transform plane. And once you do that, that provides you the second set of condition at the wall that is written on top. So, that is your wall normal component of velocity, but then we need to now also worry about 2 sets of boundary condition in the free stream. Whatever may be their functional form, we could actually transform them in the spectral plane, alpha and omega plane, and if the u velocity component in the alpha omega plane is called b, and the v velocity component in alpha omega plane is called d, then we have these two additional equations. This is what we discussed. Now, of course, then this completes the description of the boundary condition that will enable you to really fix this constant C matrix. That would be given in terms of a 4 by 4 matrix operating on the unknown constants is equal to the excitation. So, whatever may be the excitation, that is put in on the right hand side. What is important though, that if these excitations are non-null, they are non-zero, then what we can do is basically I can obtain the C I vector is equal to phi inverse of this. So, what we are finding once again is very simply this, that determinant of phi somehow is going to come into play, and the phi matrix was given in terms of the 4 fundamental solutions. Since we know the exact structure of the fundamental solution in the free stream, we could write down this last 2 rows very explicitly. However, inside the shear layer we have no direct way of finding them out analytically. So, at the wall we do not know them, but we just know their functional form, that they will be in terms of the 4 components, and we left them as they are. Now, since this free stream excitation would be imposed at a very large y, then what happens is we can see that some of the parts can go to 0. And in this context, I started telling you a story how we came to this route. We came to this route because we were interested in what we have called that upstream propagating mode. Any upstream propagating mode here refers to those modes for which the phase is moving upstream. So, if the phase has to move upstream for a real frequency, that would imply alpha r should be equal to negative. So, basically we are looking out for those elusive poles on the left half plane, which I told you in the literature, wherever they are marked with a question mark, that we do not know. Fortunately, sometime during mid-90s, here itself we figured out how to obtain them. Well, it goes a little farther back, but let us not go make it a exercise in history, but let us say that we are in the process of finding out the eigenvalues on the left half plane in the alpha complex plane. So, basically what we are talking about, alpha r is negative, alpha I could be plus or minus, right. So, we are basically looking for eigenvalues, those are given by real alpha less than 0, and real q is always obtained in a mathematical sense. So, that will always be positive, and then what we could do is we could immediately see that these 2 modes phi 2 and phi 3 outside the shear layer, that is when capital Y goes to infinity, they are the ones which actually decay with Y, right. What happens? Phi 1 and phi 4 would complementarily will support the free stream condition. Okay, that is what we are saying, that we should be able to use that, and that was the reason that we decided to keep all the 4 fundamental solutions, which should fix your this thing. So, now if we decide to look for those kind of modes for which real alpha is positive, negative, and real q is positive, then phi 2 and phi 3 are the decaying modes, and these 2 entries will go to 0 when y goes to infinity, right. It is a subdominant quantity, because you have e to the power plus alpha y. So, alpha r is positive, so it will decay with y. So, that is what we are doing away with these 2 and putting their subdominant component as 0 itself. Now, once we obtain this, we have seen the characteristic determinant is given by the determinant of this capital phi matrix. So, that gives you basically the dispersion relation. So, what's it's a kind of a wonderful simile here, that when we open it up and simplify, what we find that those growing modes with y gives rise to this part of the dispersion relation, and this part of the dispersion relation, what does it say? Well, they cannot be 0, right. What can be 0 is this quantity, And what is this quantity? This quantity is nothing but your y1, the compound matrix variable, compound matrix variable at y equal to 0. Okay? So, this is how we get. So, basically then we have learned a very interesting lesson that even when we are looking for the mode in the left half plane, all we need to do is look at the same characteristic determinant, same dispersion relation composed of the decaying modes alone. And I told you a story that we figured it out in late 80s, and we were really not very sure how to interpret it, but today now we can interpret it. You know what we are doing. Now, you see, we have talked about the historic development of the subject per se, that while the German school was very vehement in their pronouncement that there is an instability problem, but experimentally it was never been obtained. And one of the experiments was done by G.I. Taylor, and what he did was he took a flat plate boundary layer, and in the middle of the tunnel put in a kind of a vibrating bump, and that bump was oscillating at a fixed frequency, and he could not detect any wave solution, and he pronounced that this theory would not be correct. However, people later on understood that there was this mismatch between the theory and the experiment. Theory sort of sought out eigenvalues for moderate frequencies in the orders of tens and hundreds, whereas Taylor's experiment, the bump was excited only at 2 to 5 hertz. So, there is a mismatch that gave rise to this kind of acrimony between these two groups. However, this was reinvestigated again in early 90s by a group in Cambridge. Mike Gaster was looking at it, and they had a very nice clean tunnel, noise-free tunnel, and they tried to replicate the experiment done by G.I. Taylor. So, what they did was they put in a bump where the local Reynolds number based on displacement thickness is 1196. Okay. And they also basically vibrated the bump at a low frequency, and a very strange thing appeared. The strange thing that appeared was this, that you did not, once again people did not see any wave per se, but what they saw, that the whole shear layer went up and down, as if the boundary layer is breathing. That is why these are called breathing modes. So, as if the whole boundary layer is heaving up and down, and this breathing mode was also investigated by another group, that same famous group at NBS Washington. Klebanov studied this. So, Klebanov noted that if you look at a flow with noisy free stream, then you see this whole boundary layer does this. So, he was the one who also called this as a breathing mode, but now it is named after Klebanov, and this is called the Klebanov mode. So, basically now what we find that two disparate things. On one side you have the experiment of G.I. Taylor repeated by Mike Gaster, which was showing this boundary layer heaving up and down. And then there was this experiment done by Klebanov in late 50s, where the whole boundary layer was once again seen heaving. But then you're talking about free stream turbulence. It's not a monochromatic excitation like vibrating a bump. So, how these two disparate things are unified, that is what we started looking at. Well, you have seen that most of our earlier results, we have focused our attention on Reynolds number of 1000 and the circular frequency of 0.1 non-dimensional. So, what we did was we seen that for that combination we have 3 eigenvalues, okay? And those 3 eigenvalues are of the following nature. One of them is unstable, 2 of them are stable. Now, what happens is, if I start from that circular frequency of omega naught equal to 0.1 and start reducing the circular frequency, then what happens is, one by one the eigenvalues disappear. So, for example, this mode 2 that we talk about, so that is what this value is. So, this is a alpha r positive value. Then when we keep reducing omega, omega is plotted along the x axis, it goes down and then all of a sudden it disappears, the second mode disappears. Similar thing happens to the third mode, but this disappears at a somewhat of a lower wave number. And the first one, which corresponds to your TS mode, so this corresponds to the TS mode, that also eventually disappears. So, below this frequency apparently you do not have any eigenvalues, and this is a very curious thing to happen, and people did not know why there is not a stability theory for very low frequency excitation. And we here at Kanpur decided to explain it, and that is how I am going to narrate the story to you. Now, as we talked about, the alpha I variation will tell you that this is a negative value, okay. This 1 corresponding alpha is negative, but if you keep reducing the frequency, it becomes positive before it disappears. However, whenever they disappear, you do those calculations like the way we have just now talked about, you see that you get a mode with alpha r negative, and this is what we just now studied. So, what happens is that along with modes whose phase propagate downstream, we always have one mode at least we can see whose phase actually propagates upstream, and this is always there. So, when these disappear, this will still remain. So, if you are at the extreme here where there are no downstream propagating mode, only upstream propagating mode, you start with that solution, and what you can do is now you can keep increasing the frequency. You keep increasing the frequency, you come up to this point, it does not go back, it remains there. So, this actually shows that this quantity, that this curve that you see is always there, irrespective of whether those are present or not. What may happen is that these modes are just abruptly disappearing. And in the previous slide, actually I indicated to you what is really happening. What are these frequencies where this progressively one by one the mode disappears. The second mode disappeared at 0.06, the third mode disappeared at 0.027, and the first mode disappeared at 0.0026. Believe me, this is the kind of value where below which Taylor did his experiments. And when we did those calculations corresponding to Gaster's result for 1196, we found those values. So, what is happening here is if your Reynolds number is increased, the frequency at which the disturbance disappears, well, reduces even further, right. But they do all disappear, and even for this you only have these 3 modes to begin with. Okay. So, we have gone to this, and now you wanted to know the properties of other properties of these modes. For example, if you plot the phase speed and the group velocity versus omega, this is how it looks like. So, the second mode actually it goes there, and you see before it disappears, it takes a value of 1. What does it mean? The phase speed is equal to u infinity. So, this is a very interesting observation. Then you notice that before disappearing, all the modes actually take a value of 1. So, what happens is you can do this eigenvalue analysis, and you see the moment the C approaches 1, you are virtually sure that sooner or later it will disappear, and it has happened. This is a slightly sort of a failure in drawing it correctly. It is actually up to 1. So, all these modes, whenever C phase equal to u infinity, those modes disappear, while these modes are always there, and you can see they have a negative value, and you look at the corresponding group velocities, and you find that group velocity is also negative for this branch, lower branch, okay, while the upper branches, they are all positive. Now, if you now go back and look at the alpha I plot, that should really help you understand what is happening, because the alpha I for this upstream propagating mode is negative and a very large value comparatively. So, one would be really worried if one were to just look at this result in isolation, thinking that these modes are highly unstable. If you use the same yardstick like what you do for Tolman existing wave, and it was for that reason I told you, someone advised me to use Whitener and not pronounce the existence of this mode, because you cannot explain. But unfortunately, this is a legacy of trying to follow each other's work. What you actually should do is to calculate the group velocity. So, if you calculate the group velocity, what you find that those modes in the left half plane have a value of less than 0. So, that means what? These modes are propagating really upstream. So far, we have been talking about phase propagating upstream, but now we are seeing that disturbance also propagates upstream. Now, corresponding to that, if alpha is negative, then what do you have? You do not have a stable mode, you do not have an unstable mode. They are actually stable mode, and their stability is pretty high, because the alpha I values are minus 0.035, whereas if you recall for r equal to 1000, omega naught equal to 0.1, the value of alpha I for the TS wave was something like minus 0.0027 something, minus 0.007, whereas this is minus 0.035. So, it is almost like a huge 20 times more, but then these are damped modes. So, what happened is that we figured this out in mid 90s, and we are pretty happy that we could actually explain those modes in the left half plane, and we also found that for Blasius boundary layer, these modes are not very harmful, they are docile. So, nothing greatly different happens, and that is why probably people were not alerted. If it was something like this was unstable mode, somebody would have also seen it in some experiment. It was not seen. However, I must tell you one thing though, that this unstable mode, this upstream propagating modes that we found, this is for Blasius boundary layer, 0 pressure gradient. The scenario may not remain the same if you look at flow with pressure gradient, especially when you look at adverse pressure gradient flow. There you may find your upstream propagating modes can become unstable, right? It can become unstable. In fact, one of my serious thinking about the whole topic of separation is that separation happens because of this phenomena, that you have upstream propagating unstable modes. This has to be systematically done. We have not looked at it seriously, but let me tell you that if we focus our attention to flows with different pressure gradient, we may actually find out more interesting properties of upstream propagating modes. Now, here what we are showing you basically these 4 properties that we talked about, alpha r, alpha I, C phase and the group velocity for 3 different Reynolds number that has been shown. I think one of the curve corresponds to The one corresponds to Reynolds number of 400, the middle one is probably 1000, and this is 4000, like the one that you saw. The local solution also we plotted for this 3 Reynolds number. What you notice that when you look at alpha r, when you look at alpha r, they are kind of banded together. So that's a very interesting observation, that irrespective of the spread of Reynolds number, you would always have upstream propagating modes, and the wave number is kind of banded together. Okay. Of course, this x axis is omega naught, and as omega naught increases, you can see the value of alpha I is decreasing. What does decrease in alpha I mean? Alpha r means you are going to create waves of larger and larger wavelength. So what happens is, this is the property of your upstream propagating mode. We have plotted up to omega naught equal to 1, and it kind of affects the boundary layer almost similarly. Only thing is, the wavelength of those disturbances keep increasing. However, if you look at alpha I, that is somewhat revealing. For the same omega naught, you can see for higher Reynolds number, alpha I is smaller, meaning what? These are all stable, but higher Reynolds number means less stable. So if you are looking at this upstream propagating modes, at lower Reynolds number, you will not see their effect very much, because the damping rate is very high. But as you go to the later part of the boundary layer, where Reynolds number is increasing, there this damping rate comes down, and you would be able to see those. And this might somewhat tell you of what Klebanov might have been seeing. If you take a wind tunnel of a very long stretch, so you are going to simulate very large RE towards the downstream end, and there what you would find that upstream propagating modes will be unstable. See, basically, what are these upstream propagating modes? How do they come about? They came about because of those aperiodic convecting vortices that we consider in the formulation. If we don't have that, we don't get this upstream propagating mode. You must now realize that those upstream propagating modes have their cause in those convecting vortices. So if I don't have those convecting vortices, I won't have upstream propagating mode. So if I am looking at a tunnel with a dirty flow, then those vortices, discrete vortices going over the plate would give rise to some of these modes. And you can actually see the various values of phase speed and group velocity will tell you they are indeed upstream propagating. So interestingly enough, higher frequencies, when you go to the extreme right, that corresponds to omega naught equal to 1, and there the group velocity actually reaches close to a value of -7. So you can see that means what? These disturbances are going at 7 times the u infinity. So they go rather rapidly, very, very rapidly. Whereas in the lower frequency part, they do go at a smaller speed. See, in the top scale, I think probably you are not being able to see it clearly. This is -0.1, and this is about 7, -7. So they do actually go slowly. They have very lower decay rate. You can see these have pretty much close to 0 value. So upstream propagating modes would be there if you are looking at thinking of the flow in terms of a forced excitation. This convecting vortices would give rise to that kind of a sort of a footprint, which is what we are seeing here. The low frequency part would have persistent long short wavelength, which as you go along this side, well, their growth rate, the decay rate goes up, but their stretch becomes long. So, you should be able to mentally construct what you see in an experiment or in a direct numerical simulation with the help of information like this. Okay. So, now we still haven't answered that question. What happens to those cases where none of the downstream propagating modes exist and the whole boundary layer heaves up and down? Can we explain them? Well, so far what we have done, we have shown you results for two-dimensional disturbance field. But who says that the flow field cannot be three-dimensional? So, you see, asking some pretty much innocent questions sometimes helps. So, I had a BTech student, very bright and philosophic in outlook. So, I told Vivek that, Vivek, let's investigate, figure out that if it is indeed the case that these two gentlemen in 1939 and 1994 come to the same observation, there must be something to it, and we cannot just simply throw up our arm and say that no theory exists. We have to do something about it. So, we said, look, we will work it out almost like a signal problem, but now we will consider the disturbance field as 3D. Okay? And then work out what happens. Now, basically whenever I do some experiment in a wind tunnel, it has sidewalls, right. So, the distance between the two sidewall can be at most 2 nodes. So, that will be half the wavelength, right. So, I can actually find out the tunnel width, multiply by 2, and I get a spanwise wave number. Wavelength, I will call it lambda z, and the corresponding wave number I am calling it as beta naught. Right. So, what we do is that then I could write down, let us say, the v component of velocity as a combination, linear combination of all these modes, because that is the maximum wavelength I can do. I can also create it superharmonics, and that is what we have done here. We have obtained beta naught, and then we say, look, there should be a spanwise harmonic component which we will write as n beta naught, and n should be summed up from 1 to infinity, because we are proposing the problem as if this whole thing is repeating infinite times outside the tunnel. You know that this is the basis of all spectral calculations. People do not spill it out, but whenever you do spectral calculations, you are in a sense outside the computing domain. Think of periodic extension of the thing that you are doing inside. This is true for all computations. That is why you may be seeing a very interesting aspect of flow computations, that suppose I have a disturbance field which is localized. Now, if I compute that flow in a domain like this, I get one result. If I do it over this, I get another result. But my disturbance field is located in the middle. What is the problem? The problem is one of periodic extension. So, if I take a smaller domain, then I am saying I have a peak here, but outside I have another, and I have infinite such thing on all sides. Now, when I increase the domain, now those periodicity has changed, and their effect of those outside ones on the interior of the flow comes down, isn't it? So, that is what you see, people always try to tell you a dud by saying that we have done this consistency check. We increase the number of points, we increase the domain, and we got the same results. They are telling you half the story. You probably should not get it like that. You should not. If you get it, then your numerical method is laced with a huge dissipation, and that is why you do not see all this. But if you are doing a good accurate calculation, you increase the domain size, believe me, your result should be different. And this is something people do not say, but let us carry on with that ansatz, that whatever we observe, it actually has its infinite periodic extension, and that is why we have this. So, you see what happened, it is a 3D problem, but we have cheated the problem. What we have done, we have not integrated over beta, we have summed over the harmonics. So, what happens is we can use this and plug it in to our 3D disturbance equation. 3D or Sommerfeld equation would be obtained, and this is how you are going to get. I would ask all of you to please derive this and give it as a submission, so that you also have practice how to get this. So, what have you done? You go through the same exercise. Instead of saying the disturbance field is 2-dimensional, you are talking about a 3-dimensional disturbance field. Okay. And then your mean flow has, let us say, 2 components, capital U and capital W. So, you are talking about a formulation here where the mean flow also could be 3-dimensional. Only difference here is that instead of the span-wise wave number beta square, we have taken those discrete span-wise wave numbers which are given by n square beta naught square, right. So, this is what we have done. So, you should be able to see that. And however, I must tell you what Taylor and Gaster did. Both of them, both these groups, well, Taylor was alone and Gaster had co-authors. In both these experiments, what was done? They took a 2-dimensional flow. So, then this formulation itself will work, but only you have to just simply knock off that capital W I. Okay. And here, of course, once again you get RE, that is the Reynolds number based on displacement thickness, and primes indicate derivative with respect to non-dimensional y. Non-dimensionalization is again done with respect to the displacement thickness. Now, what happens is we can go through this eigenvalue analysis, right. What we would get if I fix omega naught, I will get I will also fix some beta naught and I will get the corresponding alpha. So, it is basically a reducing our work. By assuming the signal problem, we are just simply looking at omega naught. By assuming span-wise periodicity, we are talking about the fixing the beta naught. For different values of n, we are going to get different. Okay. Okay. So, we are basically talking about Sommerfeld equation for the Fourier Laplace transform phi, which is the amplitude of the wall normal component of the velocity. V prime, this prime is not derivative, this is a prime, means perturbation quantity. So, please note that prime and the primes here are of different kind. V prime is indicative of the wall normal component of the velocity, and this is the generic Sommerfeld equation for 3-dimensional mean flow and 3-dimensional disturbance field. 3-dimensional mean flow is because you have u of y and w of y, right. You can split it into streamwise and a cross flow component. And disturbance field is 3-dimensional means what? We have the amplitude as a function of y, x variation is given in terms of alpha, right, and the z variation is given in terms of beta. In this case, because we are talking about an experiment in a wind tunnel, so we have done a periodicity in the span-wise direction and we know beta naught. I know the wind tunnel thickness, I can fix beta naught. And what I could do is, I can solve this equation for different values of n. So, what you are basically doing, it is a 3-dimensional problem, but you are looking at each n beta naught at a time. So, I can do beta naught, 2 beta naught, 3 beta naught, I can take all those harmonics and calculate the eigenvalue. So, whatever we have done, whatever we have learned is going to work here directly, because we have posed it as a 2D problem now, because you are looking for complex alpha, right. However, you can also see that this alpha that we are going to get is for the 3-dimensional field, and your beta is also not a fixed number, it has discrete values, but the omega that we are getting, omega is kind of real because we are talking about a signal problem. So, I can calculate this quantity, right. What I could do is I could change omega naught to omega naught plus d omega. So, the numerator I can get it, and I can correspondingly find out what is happening to my delta alpha r and delta beta r. Delta alpha r would come about from your eigenvalue evaluation. What about delta beta r? Well, we have those discrete values of beta, beta naught, 2 beta naught, 3 beta naught. So, that is your delta b. So, we can actually numerically evaluate this Vg, okay? And that is what is done, and this expression that you are seeing there, numerical evaluation of this group velocity components. Aren't these two components in x and z direction? The first one gives you the disturbance propagation in the streamwise direction, and this is the cross flow direction, right. So, you can calculate this. So, you basically need 3 eigenvalue evaluations. So, I can do it omega naught plus d omega, omega naught plus 2 d omega, and I can calculate this, okay, right. So, we can make use of that and evaluate this group velocity. And this is what you get as the result. The top figure, we have plotted alpha r versus beta r. What is alpha r? The real part of the streamwise wave number. Beta r is the spanwise wave number. But you see what happened, if my beta naught is a very small value, n beta naught will be, it's like your numerical evaluation, right. So, the discrete points have been obtained here. So, this is alpha r versus beta r, and this is alpha I versus beta r plot, and this is how we get. And what we have basically done is we have obtained say 5 such modes. That is what we are showing here, 5 such curves, and how they vary with beta r is shown here by for this 5 waves. Okay. So, now these are what? These are your Klebanov mode. Why? Because you have put in your omega naught some values which are less than that table I showed. So, maybe less than 0.002, and then I calculated this 3-dimensional modes, first 5 modes. This is the real part of the spanwise wave number, this is the imaginary part. And what you notice that imaginary part is, of course, you are seeing they are all positive. We will see that their group velocities are also positive, and then what happens? These are all damp modes. But you can see those bottom 2 curves are quite small in magnitude, that alpha I. So, their effects would be seen, while the top 3 curves have a larger values of alpha r. So, they may not really have much steam in them to take them far, because they will decay, while the last 2 will certainly do that. And what we have here is the phase speed plotted here as a function of beta r on the top frame, and this is your Vgx and Vgz. Right? Vgx is nothing but del omega del alpha r, and Vgz is del omega del beta r. Now, what you notice is that barring a very small value of beta r, it is virtually 0. So, the phase virtually does not move very much, right. So, it would appear as if the whole thing, if I look at it, look at that tunnel, the phase is not moving. So, it would appear as if it is stationary. That is what was giving us the impression of a breathing mode. We are having a 3-dimensional flow field, but C phase is virtually 0. So, we are seeing as if it is staying in the same place, but with time, because it is changing with omega naught, we have fixed it omega naught. So, the whole boundary layer is heaving with that omega naught. That is one thing. The other thing is, you look at the x component for this 5 modes, they are plotted here, and they do have some kind of numerical problem in their evaluation, and it does show that the Vg x component, the scale is between 0.6 and 1. Okay? So, 0.6 and 1. I must confess that this was done in mid 90s. Maybe somebody should cross check them again and probably obtain them with much more higher accuracy, but this is what we obtained, that these are all downstream propagating modes, right. So, downstream propagating modes, but the phase is very close to 0, that is what we saw in the top frame. The velocity with which it goes is roughly 2/3 to u infinity range, right. It's bracketed in that. But look at the Vgz component. Vgz component is somewhat very strange. For most of the beta r component, this lies there. So, it is like 0 component of the spanwise direction. That is what people have also complained or observed. What they did observe is that you take this flow plus this boundary layer, excited at a small frequency, then you see as if the whole boundary layer is heaving. If I had a Vgz component, it would have shown there is an oblique movement, but it did not, and that is also brought out rather clearly. There is some bit of crossover in some crucial values of beta r. On this side it is slightly positive, on this side is slightly negative. We still do not clearly understand what these discontinuities are. Maybe someone will in near future will look at it much more carefully, but this was a matter of great satisfaction for us that we did achieve the following things so far in this course. We started off with what everybody does, the stability theory. We have now come to a stage where we can talk about the receptivity to wall excitation. That is what we did. We talked about all those local solutions. We sorted out the issue of any arbitrary disturbance can be explained in terms of the receptivity theory that we have looked at. We also looked at what happens when we have a free stream excitation. Now, we have also answered the question of, do we have upstream propagating modes? Yes, we do. We have just now talked about what happens if the boundary layer is excited at a very, very low frequency. Your disturbance field is very special. It is not 2-dimensional, right? You get only 3-dimensional solutions. 2-dimensional, those eigenmodes disappear. However, despite the response field being 3-dimensional, it also has a very interesting attribute. It looks like 2-dimensional because Vgz is 0. So, these are all kinds of very interesting confluence of occurrence that tells you what people have noted. And it was a very, very satisfying moment for anyone to be able to explain things that one does see in experiment. And also, I did not tell you another thing is about the alpha r. Let me highlight that aspect, because that is important. You know, none of you asked me, but if you look at this top figure, this alpha r values that we have plotted, the lowest tick it has 0.304 and the top one is 0.0012. So, what we are saying is this is 0.304 3 zeros 4 and this is 0.0012. So, if I look at a behavior somewhere here, what does it mean? Alpha r is 0.30 something. What is the wavelength? What is our length scale here? Length scale is in terms of displacement thickness. So, if I have a alpha r, let us say 0.001 also, 0.001. So, what is the corresponding wavelength? 2 pi by this. So, 2 pi by 2 pi into 10 to the power 3. So, how much is it? Some 6,000 delta star. How many tunnels in the world are made where your test section is 6,000 delta star? So, if I want to see these long waves, I have to have also a facility that long. Unfortunately, there are no such facilities. What you do is you always have a smaller stretch of a wind tunnel and you always see a part of the wave. And although the phase is changing, but if you are looking at a very small stretch, it would appear the whole thing is going up and down together, but there is some variation in the elevation because it is a part of a wave, but that wave is of thousands of delta star, which the experiments have not done. So, maybe somebody listening to it can construct one such huge setup and look for this Klebanov mode. That would be a very satisfying moment. What is interesting that we now can sum up is also that in fluid mechanics do not take any standard assumptions. Standard assumptions always fall through the standard gaps. You will not be able to explain everything. Here we are seeing that for very low frequency excitation, two dimensionality is not important, three dimensionality is. So, many a times when you would be doing research in life and you would be reporting a result, you will be hitting this wall very often. They will say, so and so has already written that the flow is two dimensional for Reynolds number up to 250. Somebody will say, oh no, it is not 250, it is 280. But keep your mind open and you can see for the same flow depends on the frequency whether you are going to get a 2D excitation or a 3D excitation, right. So, please be aware and alive to the possibilities and you will always come out with very, very interesting results. Now, let me talk about some direct simulation. Now, what does direct simulation mean? Direct simulation means the following, that we are going to solve the Navier-Stokes equation. We'll solve the Navier-Stokes equation and we are solving a very interesting problem. See, so far we have talked about as if there was a single vortex going in the free stream. But suppose you have a free stream turbulence, you do not have a single vortex, but you will have an ensemble of vortex, right. So, they will go on. So, here we wanted to study a prototypical case of one such thing. To make our understanding complete, we look at a very standard model. The standard model is that we will have a train of vortices, not one, a large number of them, and let us say gap between them is fixed and the height at which they go is also fixed. So, this is basically your prototypical thought experiment that you are conducting, and then the boundary layer is developing and these vortices are going very far above. What will happen? To satisfy the 0 normal velocity, I should have a image system, right. So, this is your physical vortices, these are the corresponding image vortices. Now, because we are putting those vortices at a fixed interval, there is some kind of a spanwise scale that is imposed now in the problem. Earlier we had a single vortex, it did not have any spanwise length scale. Here we have a spanwise length scale that is determined by the gap, but they are also moving at a constant speed. So, if I have a spanwise wavelength and I have a constant speed, what am I doing? I am introducing a time scale also. So, I will stop here, we will start it from here in the next class.